A very good morning, students. Welcome to the lecture series on operating systems. In this session, we are going to discuss about scheduling algorithms. Why scheduling algorithms are needed? Coming to that, scheduling algorithms are meant for distribution of the resources simultaneously among various processes. In the uniprogramming environment or in the multi-programming environment, if multiple processes are ready to execute, then scheduling is highly essential. This scheduling is also used to minimize the resource utilization and also avoids the resource starvation. Already you are very much clear about what is starvation. So to avoid the resource starvation and to reduce the resource requirement, these scheduling algorithms are highly essential. First come first serve scheduling algorithm, shortest job first scheduling algorithm, and non-preemptive priority scheduling algorithm. All these three fall under the category of non-preemptive scheduling algorithms. Then the priority scheduling algorithm is also comprising of another version that is called preemptive priority scheduling algorithm. The preemptive priority scheduling algorithm, shortest remaining time first scheduling algorithm, and round robin scheduling algorithm. All these three fall under the category of preemptive scheduling algorithms. In addition to all of them, there are two more algorithms referred as multi-level queue scheduling and multi-level feedback queue scheduling algorithm. These two scheduling algorithms are referred when multiple number of queues are there. Very specifically, reduced queues are there. Okay, and now we are going to talk about first come first serve scheduling algorithm at first. The implementation of the first come first serve scheduling algorithm is comparatively very simple to other scheduling algorithms. And then this scheduling algorithm is fall under the category of non-preemptive scheduling algorithm, and here the CPU allocation is carried according to the arrival of the process into the main memory. For example, I have a queue. Into that, firstly P0 has entered, and then P1, and then P2. Okay, this is the order of arrival into the main memory. According to this order of arrival, the process which is going to get the CPU at first, P0 is going to get the CPU at first, because the process which has arrived into the main memory at first is going to get the CPU at first. Based on the arrival times, the processes are going to get the CPU in the case of the first come first serve scheduling algorithm. Later, it is implemented using a first in first out queue. It is implemented using a first in first out queue. And thereafter, as I earlier said, it is fall under the category of non-preemptive scheduling algorithm. Thereafter, if any of the process has entered into the queue, then immediately that particular process PCB is linked to the end of the queue or tail of the queue. Thereafter, when the CPU is free, the process is going to acquire the CPU, and then it will keep on continuous the execution until it completes the execution. No other process are allowed to get the CPU. In the case of the non-preemptive scheduling algorithm, it is very clear that once the CPU has been allocated to a process, it will release the CPU only after the completion. In between of the execution, the processor doesn't release the CPU. Likewise, here also, the processor should not release the CPU before its completion. And this first come first serve scheduling algorithm suffers with the convoy effect. What is a convoy effect? Coming to the convoy effect. So, here I have two kinds of process. For example, P0, P1. P0 is a process which needs the CPU for 3 seconds. P1 is a process which needs the CPU for 10 seconds. Then, which process is going to complete the execution at first? Compared to P1, P0 needs the CPU for a short amount of the time. So, if the P0 got the CPU at first, then P0 will complete the execution at first. But in the reality, here you can have a simple example. But at the other end, another convoy is ready to cross the signal. But convoy has a high priority to cross the signal at first. Therefore, if the convoy has been allowed to cross the signal at first, then the convoy is going to take more amount of time when compared to the single car. But unfortunately, the convoy is having the higher priority when compared to the single car. Due to that reason, the convoy is going to cross the signal at first. But the long amount of the time is supposed to waited by the car. This is called convoy effect. Convoy effect means there is a process called P0. This process P0 is having the lowest CPU burst time. And convoy is the another process. But convoy is having the high CPU burst time. Means it needs the CPU for long amount of the time. But when the long process is executing, the short process is supposed to wait. That is going to refer as convoy effect. Due to this reason, long-term process are executing with the CPU, then it leads to the starvation of the short-term process also. It is the disadvantage with the non-preemptive scheduling algorithms. And then we are going to talk about the first come first serve scheduling algorithm by computing average turnaround time, average response time, and average waiting time. For the given this problem, we are going to compute average turnaround time, average waiting time, and average response time. For this, we have been given with the three processes. P1 with the 24 seconds as a CPU burst time, and P2 with the 3 seconds as a CPU burst time, and P3 with the 3 seconds as a burst time. Means P1 needs the CPU for 24 seconds. P2 and P3 needs the CPU for 3 seconds. Now, we are required to compute the average turnaround time, average waiting time, and average response time for the given scenario using the scheduling algorithm first come first serve scheduling. Okay, now let us reconstruct the Gantt chart. And before constructing the Gantt chart, we are considering all the processes are arrived into the main memory at the same time. What the time? 0th second. Means all the processes are held in the main memory at the same time, 0th second, in the order of P1, P2, P3. Means P1 has came into the main memory at first, then P2, then P3. This is the order, but all of them are assumed to be at the same memory at the same time itself. Okay, now first of all, P1 is going to get the CPU at first. What is the CPU burst time for of the P1 process? It is a 24 seconds. So P1 is going to get the CPU for 24 seconds. Then after the completion of the execution of the process P1, P2 is going to get the CPU and it needs the CPU for 3 seconds only. So after the 3 seconds of the time, the process P2 will complete its execution. Then P3 is going to get the CPU for 3 more seconds. Means after 3 more seconds, means after 30 seconds, the process P3 completes its execution. So after 24 seconds, process P1 has completed. After 3 more seconds, means after 27 seconds, P2 has completed. After 3 more seconds, means after 30 seconds, the process P3 has completed the execution. Likewise, by the end of 30 seconds, all three processes have completed the execution. Now we are going to compute the waiting time, response time, and turnaround time for this particular problem. Coming to the waiting time. So, how much of time the process P1 is waiting for the CPU? P1 has been assigned with the CPU after the 0th second itself. Means it hasn't waited for the CPU. Therefore, the waiting time of the process of P1 is 0 seconds. And the waiting time of the process of P2 is 24 seconds. Because P2 got the CPU only after the completion of the execution of the process P1 only. So, after 24 seconds only, the process P2 got the CPU. Therefore, the waiting time of the P2 is 24 seconds. And then P3 got the CPU only after the completion of the execution of the process P2. Means it got the CPU after 27 seconds. Therefore, the waiting time of the process P3 is 27 seconds. Therefore, the waiting times of P1, P2, P3 are 0, 24 and 27 respectively. Likewise, I am going to compute the response times also. In the case of the non-preemptive scheduling algorithms, the waiting time and response time are meant to be equal. Okay, so the response time is also referred like the process P1 is having 0. Means when the process P1 got the CPU at first. Here in the case of the non-preemptive scheduling algorithms, once the process has been allocated with the CPU, then until the completion of the execution, the process doesn't release the CPU. Means the waiting time and response time both are meant to be equal in the case of the non-preemptive scheduling algorithms. So even in the FCFS also, the response time of the process P1 is 0 and process P2 is 24 seconds and process P3 is 27 seconds as like the waiting time. When does the process has been completed? That is the question of the turnaround time. The process interval held in between the process submission and the process completion is referred as a turnaround time. Coming to the turnaround time, what is the process submission time for all the process? 0 seconds. But when does process P1 has completed the execution? After 24 seconds. So 24 minus 0, which is equal to 24. That 24 is the turnaround time of the process P1. When does process P2 has completed the execution? After 27 seconds it has completed. So when it was submitted, all the processes are submitted into the main memory at the same time, right? At 0 seconds, okay, right? So it is 27 seconds. 27 minus 0, which is equal to 27. And then coming to the process P3. P3 has completed the execution after 30 seconds. And when it was submitted after 0 seconds. So the turnaround time of the process P3 is 30 seconds. Now we are going to compute the average waiting time, average response time and average turnaround time. Coming to the average waiting time. Average waiting time is process P0 is having 0 seconds and process P1 is having 24 seconds and process P3 is having 27 seconds. Whole divided by 3, which is equal to 51 by 3, which is equal to 17. 17 is the average waiting time of the given problem. In the case of the non-preemptive scheduling algorithms, the waiting time and response time, both of them are equal. So the average response time is also equivalent to 17. Coming to the computation of the average turnaround time. What is the turnaround time of the process P1? Which is 24 seconds, right? Plus, what is the turnaround time of the process P2? Which is 27 seconds. What is the turnaround time of the process P3? It is 30. So 24 plus 27 plus 30 whole divided by 3, which is equivalent to 81 by 3 equal to 27. Okay students, so let us consider the same problem in the different order of allocation of the CPU. Here the process P1 is requiring the CPU for 24 seconds, but the process P2 and P3 needs the CPU for only 3 seconds. But we are waiting for long amount of the time, means until the completion of execution of the process P1, P2 and P3 are supposed to wait, right? So this problem is referred as convoy problem. It was already known to you guys. Okay, this convoy problem is going to be addressed by considering the order of allocation of the CPU in the different order. Means I am assuming that the process have arrived into the CPU in the order of P2, P3, P1. Means firstly, P2 has came into the main memory, then P3 has came into the main memory, and then P1 has get into the main memory. Means which is going to get the CPU at first? P2 is going to get the CPU at first, then P3, then P1. Means the order of allocation of the CPU has been changed from P1, P2, P3 to P2, P3, P1. Means the short-term processes are not yet waiting for the execution of long-term processes. This is the solution for addressing convoy effect. Now, assuming P2, P3, P1 is the order of arrival of the process into the main memory. And again, all the processes have arrived into the main memory at the 0th second only. Means the process submission time is, when all these processes have submitted, after 0 seconds only. Okay, now we are going to compute the Gantt chart only. Again, firstly, P2 is going to get the CPU and how much of time is required for it? 3 seconds is required. So 3 seconds of CPU has been allocated for the process P2 at first. So after the 3 seconds of time, P2 completes its execution. Then P3 is going to get the CPU for 3 more seconds. So after 6 seconds, P3 has completed the execution. Now which is the process left in the main memory? That is P1. So P1 is going to get the CPU for 24 seconds. So 6 plus 24, which is equivalent to 30. After 30 seconds, all processes have completed the execution. No other process have been left in the main memory. Now let us compute the response time, turnaround time and waiting time again. Coming to the computation of the waiting time. How much of time has been waited by the process P0? Process P1. Coming to the computation of the waiting time of the process P1. P1 has waited until the execution of P2 and P3. That means P1 has waited up to 6 seconds. Then P2 got the CPU at first. Okay, so P2's waiting time is 0 seconds and P3 got the CPU after 3 seconds. Means after the completion of execution of the process P2, P3 got the CPU. Therefore, the waiting time of the process P3 is 3 seconds. Now, we are going to compute the response times of all these three processes. Okay, coming to the computation of the response times. Again, in the case of the non-preemptive scheduling algorithm, the waiting time and response time are meant to be equal. So, the response time of the process P1 is, when does P1 got the CPU? P1 got the CPU after completion of 6 seconds of time. So, the response time of the P1 is 6 seconds. And coming to the P2, it got the CPU after 0 seconds itself. So, the response time of the P2 is 0 seconds. And then P3, 3 seconds. So, the response times of the P1, P2, P3 are 6, 0, 3 respectively. Now, we are going to talk about the turnaround time. What is turnaround time? The time interval between process completion and process submission. When does process P1 has completed? It has been completed after 30 seconds of time, right? So, when this was submitted? After 0 seconds. So, 30 minus 0 which is equal to 30 seconds. And when does process P2 has completed? After 3 seconds, right? So, when does it submitted? After 0 seconds. So, the turnaround time of the process P2 is 3 seconds. And when does process P3 has completed? After 6 seconds, right? So, 6 minus 0 which is equivalent to 6. Now, again we are going to compute the average waiting time and average response time. Okay, coming to the average waiting time and average response time. What is the waiting time of the process P1? P1 has waited for 6 seconds, right? P2 has waited for 0 seconds and P3 has waited for 3 seconds. The waiting time can be referred like a left value of the interval. What is the left value of the interval? It is 6 seconds for the P1 and 0 seconds for P2 and 3 seconds for P3. So 6 plus 0 plus 3 whole divided by 3 which is equivalent to 3. This is the average waiting time. As earlier said, like waiting time and response time, both of them are equal in the case of the non-preemptive. So the average response time is 3 seconds as usual. And now we are going to compute the average turnaround time. What is the turnaround time of the process P1, which is 30 minus 0, that T, plus what about the P2? P2 has completed after 3 seconds, right? So 3 minus 0, 3, plus P3 has completed after 6 seconds. So 6 minus 0 is equal to 6 whole divided by 3 means 39 by 3 equivalent to 13. 13 is the average turnaround time. What is your observation? When the CPU has been allocated to a long-term process at first and then for the short-term process, then the waiting time, response time and turnaround time are expected to be high when compared to the order of allocation of short-term process at first and then long-term process. Okay, so this is the solution served for answering the convoy effect. So this is the solution is going to generate a new set of scheduling algorithm called shortest job first scheduling algorithm. In the case of the shortest job first scheduling algorithm, a process with the lowest CPU burst time is going to get the CPU at first. Means, for example, P1 is a process which is having 3 seconds as a CPU burst time, and process P2 is having CPU burst time as 5 seconds. Then based on that, P1 is having lower CPU burst time compared to P2. Means P1 is going to get the CPU at first. P1 is a process which is having the CPU burst time as 3 seconds and P2 is a process having the CPU burst time as 5 seconds. Means compared to process P2, P1 needs the CPU for lower amount of the time. So the process with lower CPU burst time will get the CPU at first in the case of the shortest job first scheduling algorithm. And thereafter, if two of the processes are having the same CPU burst time, then the time will be break up using first come first serve scheduling algorithm. Like P2 is a process needs the CPU for 4 seconds and P3 is a process needs the CPU for 4 seconds. Then the CPU is going to be allocated for process P2 at first, because as per the first come first serve scheduling algorithm, the process which is came into the main memory at first is going to get the CPU at first. So P2 is going to get the CPU at first when compared to the process P3. Then it is also an example of non-preemptive scheduling algorithm, like first come first serve scheduling algorithm. And then first come first serve scheduling algorithm is limited with a problem called convoy effect. This convoy effect has been resolved using a shortest job first scheduling algorithm. And when compared to the first come first serve scheduling algorithm, shortest job first scheduling algorithm is having minimum waiting time, minimum response time, and minimum turnaround time, and which is optimized when compared with the other kind of scheduling algorithms like first come first serve scheduling algorithm and priority scheduling algorithm. And let us have the same kind of problem again. Means process P1 needs the CPU for 24 seconds, and P2 needs the CPU for 3 seconds, and P3 needs the CPU for 3 seconds. Okay, now we are going to assign the CPU for the process with lowest CPU burst time at first. Which of the process is having the lowest CPU burst time? P2 needs the CPU for 3 seconds and P3 needs the CPU for 3 seconds. There is a tie, right? If the tie is there, then the tie is going to be break by first come first serve scheduling algorithm. Which of the process has came into the main memory at first? It is P2. So P2 is going to get the CPU at first. And then after 3 seconds of the time, the process P2 has completed the execution, right? Now, which of the process is going to get the CPU at next? Now, P3 is going to get the CPU at next. After 6 seconds of the time, the process P3 has completed the execution. Now, only one process is left in the main memory. What it is? It is P1. Therefore, P1 is going to get the CPU at first, at next, and it is going to complete its execution after 24 seconds of the time. Now, we are going to compute the waiting time. Coming to the computation of the waiting time, when does the process P1 got the CPU? P1 got the CPU after the execution of P3, means after 6 seconds of the time, the process P1 got the CPU. Okay, after 6 seconds of the time, the process P1 got the CPU. So the waiting time of the process P1 is 6 seconds. And when does process P2 got the CPU? P2 hasn't waited for the CPU, it got the CPU at first, right? So the waiting time of the process P2 is 0 seconds, and then process P3 got the CPU after 3 seconds of time. So the waiting time of the process P3 is 3 seconds. As I earlier said, like the waiting time and response time are equal in the case of the non-preemptive scheduling algorithms. So the response time is again the process P1 is having 6 seconds, P2 is having 0 seconds, and P3 is having 3 seconds. Coming to the computation of the turnaround time, when does process P1 has completed the execution? After 30 seconds. When does it submitted? After 0 seconds. So the turnaround time of the process P1 is 30 minus 0, which is 30 seconds. And then process P2 is 3 minus 0, which is equivalent to 3 seconds. Process P3 is 6 minus 0, which is equivalent to 6 seconds. Coming to the computation of the average waiting time, average response time, and average turnaround time. What is the waiting time of the process P1? P1's waiting time is 6 seconds, plus P2 waiting time is 0 seconds. P3's waiting time is 3 seconds. Whole divided by total number of the process is 3, which is equal to 9 by 3 is equal to 3 seconds. Okay, students, let us compute the response time. What is the response time of the process P1? P1 has waited until the completion of execution of the process P3. When does process P3 has completed? After 6 seconds process P3 has completed. Means P1 has waited up to 6 seconds of the time. So the first response of the process P1 is 6 seconds. Then what is the waiting time of the process P2? P2 is firstly assigned with the CPU, right? So the first response has been given after 0 seconds. Therefore the response time of the process P2 is 0 seconds. Then what about P3? P3 has got the CPU after the execution of P2. Means P3 got the CPU after 3 seconds. Therefore, the average response time of the process P1, P2, P3 is 6 seconds plus 0 seconds plus 3 seconds whole divided by 3, which is equal to 9 by 3 equal to 3. Average response time of the entire system is 3 seconds. Likewise, let us compute the average turnaround time. Coming to the computation of the average turnaround time. When does process P1 has completed? P1 has completed after 30 seconds of time, right? What about P2? P2 has completed its execution after 3 seconds. When does P3 has completed the execution? After 6 seconds. Okay, coming to the average turnaround time, which is 30 seconds plus P2 3 seconds plus P3 6 seconds whole divided by 3, which is equal to 39 by 3 equal to 13. Okay, so the average turnaround time is meant as 13 seconds, and which is compared to very minimum than first come first serve scheduling algorithm. So shortest job first scheduling algorithm is meant to resolve the convoy effect, and as well as which is having lowest waiting time, response time and turnaround time. Now let us discuss about the another scheduling algorithm called priority scheduling algorithm. This priority scheduling algorithm is described under two modes. One is preemptive priority scheduling algorithm and other one is a non-preemptive priority scheduling algorithm. First of all, let us talk about what is a priority. Priority is a number, a small number. Okay, if the number has been assigned, according to that priority number, the CPU is going to be allocated. Like in our rank, there is a rank 1. Rank 1 is high or rank 100 is high, rank 1 is high. Likewise, the priority is going to be assigned according to the number. The lowest number is going to have the higher priority and higher number is going to have the lower priority as like our rank. Okay, now a process is having a priority number. Thereafter, the process with lowest priority is going to be described with process with a high priority number. Likewise, a high priority process is going to be described like process with a low priority number. Thereafter, the CPU is going to be allocated at first based on the priority number. Means the higher priority process is going to get the CPU at first when compared to the low priority process. And as I earlier said, like it is there in two of the modes. One is the preemptive mode and other one is the non-preemptive mode. And then shortest job first scheduling algorithm is also fall under the criteria of the priority scheduling algorithm. How do we say? Means in the shortest job first scheduling, the CPU is allocated according to the priority called CPU burst time. Means a process with lowest CPU burst time is having the higher priority, right? So a shortest job first scheduling algorithm is also one of the priority scheduling algorithm. Priority scheduling algorithm suffers with a problem called starvation. What is a starvation? I will give a simple example regarding this. For example, P1, P2, P3 are the three processes, and P4 is another process. Why I am defining that P4 is a separate means P4 is a low priority process, but P1, P2, P3 all are high priority jobs. Okay, now P1 has been assigned with the CPU at first because it is a high priority job. Thereafter, which is going to get the CPU at next? P2 is going to get the CPU at next, and then P3. Means until the execution of the P1, P2, P3, what about the P4? P4 is supposed to wait. Means that infinite waiting is referred as blocking, and for some other terms it is also called as starvation. The execution of the low priority process will be suspended until the execution of all high priority jobs. This is referred as a starvation. Starvation means the execution of the low priority job will be blocked for infinite amount of the time. That is called starvation. This is the only problem with the priority scheduling algorithm. This problem is going to be addressed through a solution called aging. Aging is a solution used to address the problem of starvation. How it is going to carry? For every fixed interval of the time, the priority of the process is going to be improvised. Then it is referred as an aging. Means, for example, I have three processes called P1, P2, P3, and whose priority numbers like 1, 2, 3. Okay, for every fixed interval of the time, the priority of the process is going to be improvised. Means after 1 second, the priority of the process P2 is going to be improved. Improved in the sense the priority number is supposed to be reduced, right? So P2's priority is going to be reduced to 1, and then automatically the process P3's priority is also reduced to 2. Okay, after the completion of another interval of the time, the process P3's priority will be further improved. Means the 2 will be changed to 1. Likewise, for every fixed interval of the time, the priority will be improvised. That is the best solution provided for the problem of starvation. And what it is called, sir? Aging. Aging is referred as a solution to address or to resolve the limitation of starvation. Let us have a small problem over the priority scheduling algorithm. Okay, it is non-preemptive priority scheduling algorithm. Let us have the discussion about the preemptive scheduling algorithm in the next phase. Okay, first of all, for a P1 is a process which is having the CPU burst time as 10 seconds, and P2 is a process with the CPU burst time as 1. P3 with 2 seconds, P4 with 1 second, and P5 with 5 seconds. In addition to this CPU burst time, you have been given with another parameter called priority. If the priority has been given, what is the priority number? The priority of the P1 is 3, P2 is 1, P3 is 4, P4 is 5, P5 is 2. Okay, from all these priority numbers, what is our realization? P2 is a process which is having the lowest priority number, means a high priority process. P5 is having next priority, then P1 is having the next priority, further P3, further P4. Which of the processes is having the high priority number? That is P4. Means P4 is referred as a low priority process. From this consideration, who is going to get the CPU at first? The high priority process is going to get the CPU at first. From this, it is very clear that the process P2 is going to get the CPU at first. How much of time we are going to allocate the CPU for process P2? P2 is going to be assigned with only 1 second of time. So, after 1 second of the time, the execution of the process P2 will be completed. Then, P5 is going to get the CPU. How much of time it needs? It needs the CPU for 5 seconds of time. So 1 plus 5, it is 6 seconds. After 6 seconds of the time, who is going to get the CPU? The process P1 is going to get the CPU. P1 needs the CPU for 10 seconds of time. So 6 plus 10, 16 seconds. After that, P3 is going to get the CPU for 2 seconds of time. Means after 18 seconds, the process P3 will complete the execution. Then P4 needs the CPU for only 1 second. Means after 19th second, all 5 processes have completed the execution. Now, let us compute the average waiting time, average response time, and average turnaround time. Coming to this, what is the average waiting time? First of all, what about the process P1? Process P1's waiting time is 6 seconds. Then P2 has waited for 0 seconds. P3 is waited up to 16 seconds. P4 has waited up to 18 seconds. P5 is waited up to. Okay, coming to the average waiting time. What about the average waiting time? Average waiting time of the process P1 is 6 seconds, P2 0 seconds, P3 16 seconds, P4 18 seconds, and P5 1 second. Total whole divided by how many of the processes are there? 5 processes are there. So divided by 5 equal to 6 plus 0 plus 16 plus 18 plus 1. 19, 35, 41. 41 whole divided by 5 equal to 8.2 seconds. As earlier said, like in the non-preemptive scheduling algorithm, the waiting time and response time both are equal. Therefore, the response time, average response time is also equivalent to 8.2 seconds. Now, let us compute the average turnaround time. Coming to the average turnaround time. First of all, let us compute the turnaround time of individual process. When does process P1 has completed? P1 has completed the execution after 16 seconds. What about P2? P2 has completed the execution after 1 second. P3 has completed the execution after 18 seconds. Then P4 has completed the execution after 19 seconds. What about P5? P5 has completed the execution after 6 seconds. Likewise, we have computed the turnaround time of individual processes. Further, I am going to compute the average turnaround time. What about the average turnaround time? The process P1 turnaround time is 16 seconds, P2 1 second, P3 18 seconds, P4 19 seconds, and P5 6 seconds. Whole divided by 5, which is equal to 17, 35, 54, 60. 60 whole divided by 5 equal to 20 seconds. So average turnaround time of the given problem is 12 seconds. Okay students, hope you are very much clear about the computation of average waiting time, average response time, and average turnaround time using priority scheduling algorithm. You have been given with another problem with 5 processes called P1. You have been given with another 5 processes called P1, P2, P3, P4 and P5. Along with the CPU burst times and the priority numbers were given. Now, which of the processes is having high priority? The process with the low priority number. What is that process? P2 is having low priority. Thereafter, P3 and then P4. Why P3 and P4? Because P3 and P4 are having similar priority. If two of the processes are having the similar priority, then the tie can be break through first come first serve scheduling algorithm. Okay, so P3 and P4 are going to get the CPU at next, then P5 is going to get the CPU, further P1 is going to get the CPU. So the order of allocation of the CPU is P2, P3, P4, P5 and P1. So P2 is going to get the CPU at first and it releases the CPU after 6 seconds of the time. Further, who is going to get the CPU at next? P3 is going to get the CPU at next. What is the CPU burst time for process P3? P3 needs the CPU for only 1 second. So after 1 second, P3 is going to release the CPU. And then, who is going to get the CPU? P4 is going to get the CPU. What is the CPU burst time of the process P4? P4 needs the CPU for 9 seconds. So after 9 seconds, means 7 plus 9, 16 seconds, P4 releases the CPU. And then we are going to allocate the CPU for process P5. P5 needs the CPU for only 3 seconds. So after 19 seconds, P5 releases the CPU. Then only one process left in the main memory. What it is? It is P1. What is the CPU burst time of the process P1? P1 needs the CPU for 8 seconds of time. Means 19 plus 8 which is 27 seconds. So after 27 seconds, all processes have completed the execution. Now let us compute the waiting times. Waiting time, response time and turnaround time for process P1, P2, P3, P4 and P5. Let us talk about P1 at first. When does process P1 got the CPU? P1 got the CPU after 19 seconds, right? So till 19 seconds, P1 process is waiting for the CPU. So the waiting time of the process P1 is 19 seconds. What about process P2? P2 got the CPU at first, means it doesn't wait for the CPU, right? So the waiting time of the process P2 is 0 seconds. What about P3? P3 got the CPU after 6 seconds of time. So the waiting time of the process P3 is 6 seconds. What about P4? P4 got the CPU after 1 more second, means 6 plus 1, 7 seconds. What about P5? P5 has got the CPU after 16 seconds. So the waiting time of the process P5 is 16 seconds. As I said, like in the case of the non-preemptive scheduling algorithms, the waiting time and response time both are equal. So the waiting time of P1 is as like response time also. So 19, 0, 6, 7, 16. Then we are going to compute the turnaround time. What about the turnaround time? Turnaround time is the time interval between process completion and process submission. Here we are assuming all the processes have submitted into the main memory at 0 second only. So submission time is the same for all processes, which is equivalent to 0. Now let us talk about the completion time. When does process P1 has completed? After 27 seconds. What about P2? P2 has completed after 6 seconds. What about P3? After 7 seconds. What about P4? After 16 seconds. What about P5? P5 has completed after 19 seconds. Right? Now we are going to compute the average waiting time, average response time and average turnaround time. Coming to the average waiting time. 19 plus 0 plus 6 plus 7 plus 16, which is equivalent to 25, 32, 48. 48 by 5, which is equivalent to 9.6. 9.6 is the average waiting time. And average response time is also equivalent, right? So average response time is also equivalent to 9.6. Then let us talk about the average turnaround time, which is 27 plus 6, 33, 40, 56 plus 15, 19, which is 75. 75 by 5, which is equivalent to 15 seconds. Okay, so the average waiting time and average response time are 9.6 seconds and average turnaround time is 15 seconds. Okay students, hope you can solve this problem at your home. Thank you students for listening the lecture. In this session we have completed first come first serve scheduling algorithm, shortest job first scheduling algorithm and non-preemptive version of the priority scheduling algorithm. What is the limitation of the priority scheduling algorithm? Starvation. Okay, what is the solution preferred for the starvation? That is called aging. With respect to the time, the priority of the process will be increased through the aging solution. Okay, what is starvation? If any of the low priority process is waiting for a long amount of the time to get the CPU, then it is called as a starvation. This kind of starvation will occur in the case of the non-preemptive versions? Yes, absolutely. If any of the short-term CPU process has been waited long time for getting of the CPU, then it is referred as a starvation itself. What is the limitation of the first come first serve scheduling algorithm? Convoy effect. What is the solution preferred for the convoy effect? Shortest first scheduling algorithm is a solution preferred to avoid the convoy effect. Thank you, students.